We're going to continue now in section 5 of chapter 2. Equations, we're going to look at doing some very simple curve fitting. Actually, we're going to do straight line fitting rather than curves. There is a mathematical procedure for fitting curves to data. It's beyond the scope of this class to get into it, but we're going to look at the very simplest form of that where we're using straight lines, which uses things you've already seen before. There is a class taught here sometimes when it has enough students to make the class that uses graphing calculators to do a lot of this. Graphing calculators have built into them these curve fitting routines that you can take a set of data and choose what type of equation you want to fit to it, and it will give you the best numeric fit, the least amount of error. And normally it uses something called least squares fit, which says that the square of the error over the entire domain is the smallest amount possible. That doesn't mean that it's actually going to go through any single data point at all. It just means that if you pick any point anywhere between the beginning and the ending of the data, that you're going to be as close as you can overall. We're going to look at it from straight line point of view. And so we're going to use equations like this or the slope-intercept form. This is called the point-slope form. If you remember, you should have seen this previously. We're looking at straight lines, so it has y to the first and x to the first. In this form, x and y are the variables. M, y1, and x1 are numbers. M is the slope, what we were just talking about. You calculate it from y2 minus y1 over x2 minus x1. It's that slope of the straight line. x1 and x2 are the coordinates of a point that's on the line. So those three things are just numbers. X and y are two variables. The slope-intercept form looks like this, y equals mx plus b. M is the slope, just like above, same number. But in this case, the letter b represents the y-intercept. Y-intercept, if you remember, is the point where the graph crosses the y-axis. And so this is the value of y when the line crosses the y-axis. It's also the point where x equals 0. Same thing. Either form of the equation can be used to do the curve fitting. This one is convenient if you have a point and a slope. This one has a lot of other uses as well, and you should already remember this form for doing other things. And so that's typically used because it's more familiar. But either one will work for getting an equation from points. If you have either one of these equations, if you're given 2 points, you can get an equation. How would you do it? Well, from 2 points, you can calculate a slope, can't you? y2 minus y1 over x2 minus x1. We just did it. We calculated a slope from 2 points. That gives you the m in either one of these. If you have this value, and we said we know points, well, we know we can pick one of those and get an x and y value for that pair. And that will give me that number, and that number. That's my equation. If you're using this form, you use the 2 points to get this. But then we need to find out what that is. So in order to find that, we plug the value we calculate here and pick one of the points, put them here and here, solve for that, and then put this and this back into the equation. Either one will give you the equation. You can also find equations if you're working with parallel or perpendicular lines. So given a line, you can say, what's the equation of the line parallel to that goes through this point? Or what's the equation of the line perpendicular to that goes through this point? Yes. This one? Y equals mx plus b, slope, intercept. We're going to work with that on working with these parallel and perpendicular lines. So we're going to see that again. So the way you work with this when you're working with parallel and perpendicular lines is you have to remember that parallel lines have the same slope. That's the mathematical definition, is the same slope. Graphically, you can't be sure, but mathematically, if they have the same slope and different intercepts. So they cannot cross the y-axis at the same point, because if they cross at the same point and have the same slope, they're the same line. They're not different lines. Parallel lines have to be different lines that have the same slope and different intercepts. The different intercepts ensure they're different lines. That's what it takes to be parallel. So if we have an equation gives us a line. In this case, it's a straight line because it's a linear equation. We want to know the equation of a line that is parallel to this line, but the new line goes through that point. Now we can check if we plug this point into this equation, is this point going to lie on that line? How would you determine that? Whether this point is on this line. Put those numbers in here and see if you get a true statement. If I plug those values for x and y in here, does that make this true or false? 2 here gives 6 minus 6 plus 8. That's not equal to 5, is it? So that point is not on that line. Therefore, I can draw a line parallel to this one that goes through that point. How do I get there? Well, what did I just say about a parallel line? What does it take to be a parallel line? Or what does it take for two lines to be parallel? Two different lines with the same slope and different intercepts. So here's an equation. If I have an equation, then I can get a slope. What's the slope of that line? You should be able to get the slope of that line. What do you have to do to get the slope of that? To get the slope of this line, put it in y equals mx plus b form, which means solve this for y. So if I want to solve it for y, I'm going to subtract the x term to get it to the other side. I'm going to divide by the coefficient. That's y equals mx plus b form, right? Y equals mx plus b. Why would I want to put it in that form? I said I was looking for slope, didn't I? Why does that help? Why does this form help when I'm looking for slope? What's this number? whatever number this is the slope. So if you put it in this form, you can say what the slope is. The slope is 3/2. You can't do it in this form, but put it in this form, and then this is the slope. So the slope of that line is plus 3/2, right? How does that help me get another equation? Well, if that equation is parallel, what's true about the slope of the new line? It has to have that same value, doesn't it? Well, new equation, I've got those two forms we looked at a minute ago. One of them was like this, wasn't it? And if I said the slope is this value, that means my new equation looks like that. But that's not finished because I can't graph anything from that because I don't know what B is, do I? So I've got to find B. How can I find B? Say it again. Why are you saying x equals 3/2? This is the slope. This 3/2. This is the slope. That's not. This is the slope, the number in front. That's why it's 3/2. So this and this are going to be the same thing. You're on the right track, though. But it's not 3/2 we're going to put in there. What we're going to put in there are these two numbers. This is x and y, isn't it? That's what an ordered pair is, x and y. Here's x, here's y. If I put those numbers in, this point has to be on this line. That's what we said. The new one passes through that point. Therefore, this point has to make this equation true. So put this value in and this value in. So y is -4 equals 3/2. X is 2 plus b. Put those numbers in for x and y, and now I have an equation I can solve for b. So I have a value for b. I can take that back and put it in here now. Putting -7 in place of b, because now I know what b is. B is -7, so I can put -7 in there. Now I have a complete equation. Is this equation parallel to that equation? What does it take to be parallel? So does it have the same slope? 3/2 and 3/2, that's the same. And the other thing is what? And what are the y-intercepts? And those are different, aren't they? Therefore, those are two parallel lines. Okay, so they're parallel. That satisfies this part. Does this line go through that point? Let's put x equals 2 in here. So 3/2 times 2 is going to give me 3. 3 minus 7 is -4. So it goes through that point. So given a point and an equation, you can find the equation of the line parallel to that goes through that point. You can also find the line perpendicular. We're going to look at that next. You need to be able to do this sort of calculation. You can use either this form of the equation, or you could use this form. In both cases, you have to calculate m, or you have to find out what m is. So you still need to put this first equation in this form in order to determine what m is. But then I could take m back here and those 2 points here and here, and I'll get this same equation. So it's a little bit less work to do the second, to use this equation on the second part of the problem. There's my equation in y equals mx plus b form. On the slide, I'm using this other form. You put that number there, that number there, that number there, which gives me that, which when I rearrange it gives me that. Same slope, different intercepts, goes through that point. Either way, I showed it manually using the y equals mx plus b form. The slide shows it using this point slope form. That was parallel lines. Parallel lines, same slope, different intercepts. Perpendicular lines, you still talk about the slopes, but the relationship for the slopes on perpendicular lines is that the slopes of the two lines are negative reciprocals of each other. What does a negative reciprocal mean? Flip it and change the sign. Negative reciprocal means flip it and change the sign. So if M1 is minus 3/4, the negative reciprocal is plus 4/3. Flip the fraction over, because it's always a fraction. Remember, a whole number is over 1. So it's always a fraction. Flip it over and change the sign in front of it. This is a negative, it becomes a positive. 3/4 becomes 4/3. These are negative reciprocals. Therefore, this slope and this slope indicate perpendicular lines. That's all you have to know to determine whether they're perpendicular are the slopes negative reciprocals. If you're trying to get an equation, you're going to have to go through the same sort of procedure we just went through, except instead of the slopes being the same, the slopes will be negative reciprocals. If M1 equals 2, the negative reciprocal is minus 1/2. Because 2 is 2 over 1, flip it over, it becomes 1 over 2, change the sign. If you're given a slope of 4/3, the perpendicular slope would be minus 3/4. If you're given the slopes minus 1/2, perpendicular slope would be plus 2. So here the same point and the same equation. We want the equation in the line perpendicular now, not parallel, we want it perpendicular. So how do we go about that? Put it in the slope-intercept form, the y equals mx plus b form. Why do we need to do that? Why do we need to put this in this form? So we can determine what the value of m is. Why does this help me determine that? You're on the right track. The reason this helps is because in this form, this number multiplying the x is m. This is the slope right here. That number, whatever that number is with whatever sign it has, that is m. So you put it in this form in order to get that value. In this form, that is the value right there, plus 3/2. Okay, so, and m is what? Slope. And it's the slope of this equation, right? Slope of that line. If we're looking for perpendicular, what's our other equation going to be? What's one thing we know about that second equation? Perpendicular line means what? Reciprocal. Negative reciprocal of what? Negative reciprocal of what? Okay, and my slope I said was what? So what's my negative reciprocal? So there's the slope of my perpendicular line. But that's not the equation, that's just the slope. How do I get the equation? Actually, two paths you can follow from this point. Got two different forms of the equation. Slope-intercept, point-slope. Either one works. I normally just stick with the slope-intercept because it's most familiar to me. But you can choose either one you want. That's your slope. Both equations use that number. Which way you want to do it? Slope-intercept. Okay, I don't remember what I did here. I did both. That's point-slope, that's slope-intercept. M goes either there or there, depending on which way you're doing it. We just said that was minus 2/3, right? So we're going to put minus 2/3 there, we're going to put minus 2/3 there. On the point-slope form, it goes to the point 2 minus 4. Well, the point-slope form, x1 is 2, y1 is minus 4. I can put those values in to the point-slope form. Over here, I've got to do a little more. Put those numbers in, it gives me that. Over here, I have to put the minus 4 and the 2 and the minus 4 in those places. So I put 2 in for x, minus 4 in for y, and that gives me an equation that all I need to find out is what b is. But this gives me a way to find out what b is. Solve that, and I get b equals 8/3. Over here, rearrange the equation to combine like terms, and I wind up with this. Over here, if I put this value for b back into here, then I'll have the complete equation here. This is almost complete, except I need this value for b. This gives me the value for b, so I can plug it back in, and I have the two different ways to get the same equation. You can either do this way, or you can do this way. Either one is fine. They both give the same answer. This one's a little easier to apply, but you have to remember another equation. Whichever way works best for you, it doesn't matter. It's just that you need to be able to get this equation. So given a point and an equation, you can find the equation parallel or perpendicular to that equation. You could be given 4 points and ask the same question. Or you could be given 3 points and say, draw what's the equation of a line perpendicular to the line that goes through these 2 points and then goes through the other one. Probably you wouldn't be that involved, but it's possible to do. Because if you're given 2 points, that gives you an equation of a line. Then if you have another point, you can say what's the line perpendicular or parallel. All right, what's the slope of that line? 2 points gives you a single line, so there's a single slope. You need to make sure you know how to use that equation. It applies when you have 2 points. Given 2 points, you can calculate the slope of the line between them. So the slope of that line is 1. Can you graph that? You should be able to. There are different ways that you can do that. Probably the easiest way is plot the point and then use the slope to get another point. If it goes through this point, then that point's going to be on my line, isn't it? Where's that point? So where would that be on here? First number is the X. That's minus 2.8. I don't want to label it there. Label it here. Actually, that's the wrong place to label it also. Let me just leave it unlabeled. Slope of minus 1 means what? It's that, isn't it? It's a whole number. It always has a denominator of 1. If you're graphing and you have a point and a slope, one way to do it, not the only way, but one way. Look at your fraction that defines your slope. Move to the right the denominator number of units. Move up or down the numerator number of units. So I'm going to start at this point. I'm going to move to the right 1 unit. Then I'm going to go down 1 unit. Oops, sorry, that was 2 units. Move here and then go down 1 unit. Then I can move to the right again and down again, and so forth. And because it's a straight line, it's going to look like that. You need to be able to graph points like this, or graph lines like this. You can do it by an XY table, but then you'd have to have an equation. So if you're going to use an XY table or intercepts, you're going to have to get the equation first. That's fine. If you're given a point and a slope, you can plot this way, but you need to remember how to do it. But you need to be able to do this kind of graph. That's what it would look like neatly. Here's the point, minus 2 and 8. You can go over 1 and down 1, over 1 and down 1, and so forth. Okay, linear models. Linear models are just functions that are linear. Mathematical model defines a relationship between two things. That's a relation. We want to work with functions, though, so we get unique values. So we're going to work with linear functions. Some typical things that you might see and you might be able to relate to the real world are for a company, they have cost functions, they have revenue functions, and they have profit functions. Cost would be what it takes to make their product. That includes salaries, it includes utilities, it includes lease on their building if they have it, it includes purchasing equipment, it includes purchasing raw materials. All those different things go into cost. Revenue is how much money comes in the door. Revenue is not profit. If they sell an item for $10, they don't get $10 profit. They get $10 of revenue. So that's what they get coming in the door. Profit is the difference between the revenue and the cost. Profit can be either positive or negative. Cost is always going to be a positive number. Revenue is always going to be a positive number, but profit could be either positive or negative. They could cost more than they get selling it. That would be a negative profit. A cost function, we're going to just look at linear ones, but C for cost, and we're going to say it looks like this. It's going to be a function of X, where X is how many items are they making. So the cost depends on how many items. So there's an amount for every time you make it, you get a little bit more cost. So that includes, what raw materials go into this product, because you use those up, and those cost money. So each time you make one, you use a little more of that, and so that's an incremental cost. You also have these fixed costs. Those would be salaries, utilities, lease on your building, those kinds of things. Those are fixed costs that does not matter whether you make any or not. You're still going to have to pay those. So cost function has fixed costs and incremental costs, or changing costs. We're going to look just at a linear function. Revenue is also, we're going to look at linear. It is strictly what's the price of the item times how many you sold. So it's just a P times X. It does not depend on, there is no fixed cost or fixed revenue. You don't get something just for being in business. You only get something when you sell something. So that's revenue. Profit is the difference between those two. Hopefully it's going to be a positive number. So we're going to assume, for the sake of this class, that the number you make is exactly equal to the number you sell. We're not going to have any inventory. We're going to make and sell the same amount. M is the variable cost, because that depends on something changing. M is going to be a fixed number, but it's called the variable cost because it goes into the term that varies. That depends on how many of them you do. So M is called the variable cost. B is the fixed cost. That does not change no matter how many you make. P is the price. So that's our simple model of revenue, cost, profit functions. These are examples where you use models. Companies will go to a lot of effort to do predictions on these. That goes into building their budgets each year. How much are they going to have to pay for utilities? What are their salaries going to be? How much are the raw materials going to cost to make the items they make? If we set our profit or our prices this way, how many can we sell? If you make the price too high, you sell too few. If you make the price too low, you don't make enough money to make a good profit. So they have to use some judgment on what the right price is. Models help them look at those alternatives. by saying, okay, well, if we charge this much, that'll give us this much revenue. Therefore, our profit will be this much. So what happens if we change the price? What's our function going to look like? And therefore, what's our profit going to be? All of these get into this modeling. And larger the company is, the more complicated all of these functions become, taking into account all kinds of different things. If they're very large, they may be able to get discounts on their raw materials the more they buy. And so their cost function is not going to be the same for all X's. It's going to be different. If they have a small number, it's one thing. If it's a big number, it's a different function. And so that all goes into those kinds of models to set that up. We're going to look just at the simple one, though. So cost, revenue, function. Let's look at a particular example. We have a company, and we're going to assume everything's linear functions. If you look, all of those are linear functions. And the fixed cost is $1,500. Remember we said fixed cost was that item B over there. It's in the cost function. It's the one that doesn't change with the number that you make. So our fixed cost is $1,500. The variable cost was that number that was in the X term, and that's going to be $100. So each time we make an item, it costs us $100. We have $1,500 that we have to pay whether we make any or not. So fixed cost, variable cost. We're going to sell it for $125. So that would be the P, the price. We sell it for $125. That's the price. So cost, our cost function, our revenue function, our profit function. What are they going to look like? Well, then another one. Having all of these, what is it going to take to make a profit? When you're talking about profit, really you usually talk profit and loss. Even though it's called a profit function, you only talk about profit if it's positive. Loss would be a negative value. Break even is where that function equals zero. So the break even point is where your profit function equals zero. So M was 100, that was our variable cost. 1,500 is our fixed cost. 125 is the price we sell it for. We're going to assume we make only as many as we sell. We don't have any inventory left over. So our cost function is going to be cost equals mx plus b. Here's m, there's b. So our cost function is 100x plus 1,500. $1,500 whether we make any or not. Every time we make one, it costs us another $100 for utilities, raw materials, whatever. Revenue is going to be, if I buy a bicycle for $100, it's going to cost me $100. If I buy two bicycles, it's going to cost me $200, and so forth. So it's going to be the price times how many? 125x. Profit is going to be the difference between those two. The revenue function minus the cost function. So there's the revenue function, there's the cost function. Simplify that and you get this as your profit function. So there are our cost, revenue, and profit functions. So if this is our profit function, how many items would we have to make and sell in order to make a profit, which means make a number greater than zero? How do we get that? Well, there are our functions. We want profit to be not zero, we want it to be greater than zero. So now we have an inequality. That's okay. P is this. We know what P is, so we can put that in on the left side. That has to be greater than zero. So here's an inequality. Solve that linear inequality. So if we do that, we'll get x is greater than 60. What does that mean? What that means is 61 or more, because you can't have a fraction of an item. So you're going to have to sell at least 61 to make a profit. This is one of those things where the problem is limiting what our range is. We can't have 60.1 items. We either have 60 items or we have 61. Mathematically, we can have 60.1, but problem, we can't. So this is being limited by the problem. Remember on cost, revenue, profit functions, if it says what's the break-even point, that means your profit's going to equal 0. We would set that equal to 0. If it says what does it take to make a profit, that's going to be an inequality, so we get greater than 0, which means you round up. You don't round, you round up. You always go to a complete item. So you always round up on how many items. Otherwise, it's plug the number. If it says if you produce and sell this many, what's your profit, you plug in and calculate.
Let's look at another example. This problem, this example is exactly like the previous example, except for different numbers. In this case, our fixed cost is $2,400, our variable cost is $120, and our selling price is $150. We want linear functions to model cost, revenue, and profit. We also want to know how many items need to be sold to make a profit. And remember that making a profit means that profit has to be strictly greater than 0, not equal to 0. So in our problem, the way we had previously set it up, we had the variable cost we were going to call M, the fixed cost B, and the selling price P. Then when we create our functions, our cost function C is just mx plus b. And with m equal to 120 and b equal to 2,400, we get that our cost is equal to 120x plus 2,400. Next, our revenue is our price times the number of items sold. We're calling the revenue function R. So revenue is 150x. Price times number of items. Profit is just the difference between revenue and cost. So P equals R minus C. But we have P is this number, so we're going to put that here. And C is this expression, so we're going to put minus that here. If we simplify that, we get that P, the profit, is equal to 30x minus 2,400. So there are our three functions: the cost function, the revenue function, and the profit function. Fourth part of the problem was to calculate how many items you need to sell to make a profit. Well, in order to make a profit, this needs to be greater than 0. If that's greater than 0, then that means this must be greater than 0. So P greater than 0 means we must have 30x minus 2,400 is greater than 0. That's just a linear inequality. You solve it in the normal way. Add 2,400 to both sides, divide both sides by 30, and you get x is greater than 80. Another thing that we can do is, what if we're given a situation where we don't know what the fixed cost and the variable cost are? How can we work with that? I'm not going to go through the complete part of that, because once you have cost, the cost function and the revenue function. The profit's easy to get. What I'm going to show is how do you take a set of data and from that data get an equation. Instead of being told what M and B are, how do you get those for yourself? So we're going to look at finding the equation of a straight line that represents a set of data points. Now the set of data points can be given either in a table or they can be given on a graph, an XY graph. Both of those are sets of ordered pairs. We discussed that in earlier classes, where a table is one way of writing a function because it's a set of ordered pairs. A graph is another way. Well, what we're going to do is we're going to take individual points on a graph or individual lines in a table, use one of those, use two of those points to calculate a slope. Then using the slope and one of those points, we calculate the equation. And then we can use that equation to predict new values. So pick 2 points. And when you're doing this, if you're not told which 2 points to pick, the best way to proceed with picking the points is to graph the data points. Then visually determine which 2 points, that if you drew a straight line through 2 of the points, which 2 points would do the best job of having the line run through the middle of the data points. And you can do a surprisingly good job that way. The line that you would come up with, the points that you would choose, would be very close to what you can get with the best numeric fit that the numeric procedures give you. So pick 2 points. From those 2 points, you calculate the slope of the line. Now that you have a slope, pick one of the points. A slope and a point allow you to calculate an equation. You can use the point slope form or the slope intercept form, doesn't matter. Either one will get you the equation. Here's an example. This case, let's suppose that you're given a table of data for annual tuition and fees at four-year colleges. And it's given by year, and the tuition fees are given in dollars. What we want to do is we want to find an equation that models that data, and we want to use that equation to predict the costs in 2008. The table ends at 2006. We want to know what happens in 2008. That's what a model can allow you to do, is to find a value for 2008 that's not just a pure guess. It's going to give you a better simulation of what that value would be than just a guess. In doing this, we're told a few things to help us proceed with it. And the first thing that we're told is that we want to look in our model, let x equal 0 represent the year 1996. What that means is we're not going to use 1996 in our model to put into our. Instead, what we're going to use is we're going to use 0. And then for every year later than 1996, we're going to add 1 to this 0. So 1997 would be x equals 1, 1998 would be x equals 2, and so forth. So 2006 would be 10. On the right of our screen here is a plot of these data points. So each one of these dots is one of the points in this. So using the slope, And the 2 points, here's the definition of slope, and using the 2 points, plug the numbers in, and we get m equals 277. This time I'm going to use the point slope form of the equation, and I'm going to take this number 277, which is m, and I'm going to substitute it in here. Then I'm going to pick this point. Remember, both of these come from the same point, so I'm going to pick that point and use those values to put in here and here. So I'm going to put 277 in here, I'm going to put 2 in here, and I'm going to put 3486 in here. Which that looks like that. Simplify this, and I wind up with this equation. This equation is the equation we want to model the data from that table. In this equation, in order to use it correctly, when we use it, we must put that shifted axis, not the year, in here. We need to put that value that represents the year. So the year 1996, instead of putting 1996 in here, we would put the number 0, and so forth. So here's our equation. That was the first question we were asked to find. What's that equation? Well, that's it. Second one was we need to predict the value from the year 2008. We don't have that value in our table. This equation allows us to come up with a reasonable prediction of that. Well, if we use this idea of x, and x represents 1996, and then you add 1 for each year after that, 2008 is 12 years after 1996, therefore x equals 12. If we plug x equals 12 into here, we would get this. Do the simplification, and we get 6,256. The y value from our table was dollars, so it's $6,256. That is the value predicted for 2008. Another example, and because I didn't have room to put all of it on this slide, it's on the following slide. But what the table and graph on that following slide illustrate is the percent of women in the civilian labor force from 1960 to 2005. It's actually tabulated every 5 years, starting with 1960. From that set of data, we're asked to use these 2 points, 1960 and 2000, and those were the percentages in those years. These are actual percents, 37.7%, 59.9%. So we're actually, this is the one time when we're going to work with percents as percents rather than percents as decimals. We want to use those 2 points to find a linear equation to model the set of data. Once we have that equation, we want to estimate the percent in the year 2005. Actually, the table has the year 2005 in it, so we know the real value. We're going to calculate a value from the model, and then we're going to compare the value from the prediction with the actual value and see how far off it is. So let's look at the data. Here's the table of data. Every 5 years from 1960 to 2005, and the y value is in percent. And we're told that we're supposed to use this point and this point to calculate a straight line. And if you look at that, if you drew a straight line through those 2 points, it would kind of go through the middle. Well, actually, I'll show you what that looks like at the end of the problem. So there are 2 points. We want to calculate the equation, the straight line going through those 2 points, which will be a representation of this set of data. So we calculate the slope using those 2 points, and that turns out to be 0.555. Then we're going to take that slope, and we're going to use this point, 1960. We could pick either one of them. I chose to use the 1960 point, and we're going to get the equation of the line. This time, instead of the point slope form, I'm going to use the slope intercept form. I'm going to plug this value for m in here, and that gives me that equation. So my equation is this, but it's not finished yet because I don't know b. I have to find the value for b. The way I find the value for b is I take these two values from this point, and I put the x value in here, and I put the y value in here. If I do that, I have this. This equation then can be solved for b and get a value for b. We do that, we get b equals minus 1050.1. Now we're going to take this value and we're going to substitute it back in here. And when we do that, we wind up just with x and y in our equation. Next, we're asked to use the equation to calculate the percent in the year 2005. Well, here's our equation, and what we're going to do is we're going to plug 2005 in where x was. This case, we're actually working with the year. We're not changing from years, from the actual year to how many years after. We're actually using the year number. So we plug this in. This illustrates that you can use the year. It just gives you different values in your equation. So we plug in 2005, do the calculation, and we get y equals 62.7%. This is the predicted value of the percent in the year 2005. This came from solving the equation at that point. So that's the part B answer. What's the predicted value from the equation? Part C was to take this predicted value and compare it with the actual value. The actual value was 59.3%. The predicted value we just calculated was 62.7%. So the predicted value is 3.4% larger. Not too bad. It's not ideal, but it's not too bad. And an indication of the fact that it is pretty good is if we plot the straight line for this equation on top of the data points from the previous graph. When we do that, the straight line is this line here. It goes through that point and it goes through that point. It must, because those are the points we calculated it from. It looks like it might also go through that point, but you can't be sure without checking it. And as you can see, that straight line pretty much goes through the middle of the data. So it does a pretty good job of representing that data.